Section 10.4 has the comparison test and the limit comparison test. This is on page 606. We start with the comparison test first. This is what it says. Suppose you have Suppose you have two series in which the sequence b sub n is greater than the sequence a sub n for all n, or for some n bigger than or equal to. So after a given time. Not that it matters, I'll tell you what that means as we do problems. Then observe how this works. This is bigger than this. This says they both must be positive. It only works if the sequence part is positive. It doesn't work for negative. If both of those are positive, if the larger converge, then the smaller automatically converge. Hopefully that makes sense. If the higher function converge, it converges anything beneath it, and vice versa. If the smaller diverge, if what's smaller is going to approach infinity, then anything above it will approach infinity. So two useful cases and two useless cases, which are, if the smaller converge, that doesn't tell you anything about the bigger, and if the bigger diverge, that doesn't tell you anything about the smaller. So if this is warning, if the series of b sub n, which is larger, diverge, then nothing. And if the smaller converge, then also no conclusion. And this is how it works. I'm looking at series. Now I know about the integral test. I should try test for divergence on every problem. However, here on 1 through 8 they say use direct. Again, on your test I'm going to say does it converge or diverge. You could use any test you like. So I'm glancing at this. Again, I could use different tests on the long run. For now, let's make sure we can get this out of the way. The way it works, I suggest you start with the denominators. I suggest clearly you get rid of the numbers. Always the numbers. Now, wouldn't you say this is bigger than that? And if I was to put 1 over, then that inequality will switch. If I was to put 1 over, that will switch. Until you get the hang of it, that's what you should do. Copy everything else, so multiply by n minus 1, not a problem. So I got this going in one direction. That's very good. Now, if I get rid of the negative 1, would that still work in that direction? If it does, I'm in good shape. So did I make it bigger by taking the negative 1 away? Yes, I did. And reason for that, if you let n equal 10, 10 is bigger than 9. So again, it's going to take a bit of time to really adjust and get used to this. So now what? Isn't this 1 over n cubed? Now I do want to warn you. 1 over n cubed is a sequence. That sequence converge. We're not asking about a sequence. It's true we're comparing sequences, but we are concluding about series. So unless you put a series on that, unless you say the series, it's not a p series. Now it is. So without that summation, it doesn't work. P equal 3 bigger than 1. Therefore, converge. What did I've just shown? I have just shown that this is bigger than this, right there. And I've shown that the bigger converge. Therefore, the series n equal 1 to infinity, n minus 1 over n to the 4th, plus 2 converge by the comparison test. Now, do you have to write that every single time? And how come you never had to do that before? Because before we only had one series. We never introduced another series. Anytime you have more than one series, I need you to be very specific of what you're talking about. And if you don't write anything there, you're saying this is n equal 1 to infinity. You don't have to write that. We agreed. 44. same deal. This is not continuous at 0 or 2. It's fine. It's defined everywhere. So I'm going to take n squared minus n, and I'm going to compare that with n squared. So always get rid of one of those at a time. Which is bigger? Isn't this bigger than that? Think about it. If n equal 10, this is 90, this is 100. When you put 1 over, this switches. Again, until you get the hang of this, I suggest you do that every time. Now if I tag the rest, that is, if I tag the n plus 2, and get rid of that 2 if I can. If I get rid of the 2, the denominator is the same. Which is bigger? Isn't this bigger than that? So you want the inequality to match. And it does match. And so the goal is to get rid of the numbers and variables if you can to make it a p-series. 1 over n converge. That's a sequence. Now it's a series. This series, p equal 1, diverge. You have to say that. Now, I've shown that this is smaller than this. Therefore, the series n equal 2 to infinity of n plus 2 divided by n squared minus n diverge by the comparison test. So anytime you say converge, you have to say by what? Anytime you say diverge, you have to say by what? And another problem. Number 6. So here I have a choice. Now, if you do the wrong choice, you'll figure it out. Here you can't tell which way to go. I'm thinking n times 3 to the n. I'm thinking of getting rid of n. I'm getting rid of n, yeah. There. Wouldn't you say this is bigger than that? This is 1 over, this is 1 over, switch. Now what? You gotta be careful to put series there. This is geometric. R equal 1/3 less than 1, therefore it converge. And isn't this bigger than this? Therefore, the series n equal 1 to infinity of 1 over n, 3 to the n, converge by the comparison test. And that's how it works. You could have gotten rid of 3 to the n first. And you'll notice you'll get nowhere. You'll get a bigger and the bigger diverge. That's useless. So make sure that you're using this in the right direction. And I picked 3 more just for practice. Here it says use the series. Which of the series converge and which diverge? You could use any method you like. That's how it's going to be on the exam. So when I glance at this, I'm looking at 1 plus the cosine of n. Now the one thing I didn't mention, I have to make sure, I did mention, those have to be positive. So make sure that these are all positive, right? For n equal 1, even the 0 is neutral, it's okay, I'll let it slide. Because if you use it and those are not positive, then you get no credit. They have to be positive. Now, looking at sine and cosine, I know the biggest a sine or a cosine could ever be, and what would that be? What's the biggest a cosine could ever be? Isn't that a 1? So that is 2 over n squared. Series. I could take the 2 up front if that's bothering you, but either way, I'm looking at a p series. P equal 2 bigger than 1, therefore this series converge. And if the bigger converge, therefore the series n equal 1 to infinity of 1 plus the cosine of n over n squared converge by the comparison test. It looks simple. Well, it becomes simple when you do enough. And luckily, I'm giving you more than enough for homework. So first I get rid of numbers. Sine and cosine are easy to eliminate. In this case, I'm looking at n plus 1 over n squared radical n. And do you see that if I get rid of the number, there's only one number, wouldn't this be bigger? And wouldn't this n cancel with that n one time? So isn't that n to the 3 halves? Well, that didn't work. Well, that's not working because there's no point in going on. I could say that's the series p equal 3 halves bigger than 1, therefore converge, but this is smaller. So be careful, this is useless. Instead, can't I split this up? Can't I say this is actually the series n equal 1 to infinity, right? So here, there's no point in me going on. Can't you say this is the series of n over n squared radical n plus the series n equal 1 to infinity 1 over n squared radical n? And wouldn't you say this is the series n equal 1 to infinity of 1 over n to the 3 halves plus the series n equal 1 to infinity 1 over n to the 5 halves? Isn't this p equal 3 halves bigger than 1, therefore converge? Isn't this p equal 5 halves bigger than 1, therefore converge? Right, so you're done. Here I didn't compare it to anything, I just showed that this series converges. So just make sure that you don't fall into this comparison test works on. If there was one test that works on any series, they would have gave it to you and called it a day. How about 26? If I look at n cubed plus 2 and n cubed, I always get rid of numbers. This is bigger. When I put 1 over, that switches the sign, put the square root. This is 1 over n to the 3 halves. That's good news, even though that's 3 halves, but this is bigger. So that makes a difference. P equal 3 halves bigger than 1. Therefore, the series n equal 1 to infinity of 1 over the square root of n cubed plus 2 converge by the comparison test. Now, I get to problem number 10. And on problem number 10, oh boy, there it is. Problem number 10, I get into a dilemma. I say, alright, let's see. If I take n squared plus 2 and n squared, well, this is bigger. 1 over 1 over, we'll make that less than. N plus 1 under a radical, no biggie. What's going on? That's not working. What if I got rid of the number at the top? Well, you could. You could say, let's look at n plus 1 and n. Well, this is bigger. Over n squared plus 2 over n squared plus 2 under a radical. Again, if I look at this, if I get rid of this number, then that's going to switch. Well, what can I do? I could use the integral, but I know this is lengthy, so I get stuck on a problem I'm not sure what to do, and that's where the next test comes in handy. We are gonna look at the next test and only take a portion of it. So we're not taking the limit comparison test as it is in the book, we're just taking the first case. And there's a good reason for that. So, limit comparison test says if we have two sequences that are bigger than 0, for some number, it doesn't have to be always, but after a given time. You know, for example, if you look at x to the 10th and e to the x. E to the x will eventually dominate, but not in the beginning. You know, at x equal 2, for example, 2 to the 10 is much bigger than e squared. You know, 3 to the 10 is much bigger than e cubed, but eventually the exponential is going to dominate over the polynomial for certain x or n. So, as long as these both are always positive for certain values, right? And the limit as n approaches infinity of the ratio of those two equals c. So let's go back to section 7.4, right? If you remember the related growth, if you recall how that works, what happens if I get the limit to be a number? That's this case. That means that f and g grow at the same rate. So we're not going to take this test and make it into 3 different sections. We're going to make it one simple test. Keep in mind, when I take the limit of a sub n divided by v sub n, and I get that to equal a number, and this number is positive, one, it's guaranteeing that both of those are bigger than 0, and it shows that those two are growing at the same rate. So either they both converge or they both diverge. So they're only giving me one. They're only giving me a sub n every single time. This is a sub n. I have to come up with b sub n. So I'm working backwards to ensure that this limit will be a constant. I'm going to look for dominance. What dominates over the top? Isn't the top dominated by n? How about the bottom? So I'm really taking the dominance term, and by doing that, I'm ignoring all the numbers which could show a challenge in coming up with a less than or a greater than, to use the comparison test. So isn't this 1 over n to the 1/2? Well, that's not enough. You have to show the series, not the sequence. P equal 1/2 less than 1. Therefore, this diverge. Now, I already know that when I take the limit as n approaches infinity of the given divided by b sub n. b sub n is any of those. If you really want to save time, stick with this. Divided by the square root of n over n squared. That's the limit as n approaches infinity of the square root of n plus 1 over n squared plus 2 times the square root. Actually, I could use 1 over n, right? That's the same thing. So that's n. N over 1. And wouldn't that be the limit as n approaches infinity of the square root of n squared plus 1 over n squared plus 2? Limit as n approaches infinity divided by the highest power term of the denominator. And wouldn't that limit equal 1, which is bigger than 0, 1 over 1? What's your conclusion? Your conclusion out of this, therefore, they both what? They both, in this case, diverge by limit comparison test. So, if you missed that, this is the idea. I'm given a single series. When they say if you have 2 series, you have to come up with this second series. You have to make that up. For us to ensure that this limit is a constant, we have to make sure that this is growing at the same rate. All what we do is take the dominance term of the top and the bottom, and there it is. I'll come back to 16 in a minute. I want to go to the next problem. Again, I'll come back to 16. Just give me 1 sec. This is another problem. This proves a bit of a challenge to really find something bigger than or less than. Meaning, if you start with n plus radical n, and you say n, well, this is bigger for sure. If I go 1 over, the 3 doesn't change anything. Doesn't this diverge because p equal 1? But this is bigger. Well, that didn't work. Okay, what if I go the other way? N plus radical n. Radical n. This is bigger. 1 over will switch the symbol. And this is p equal 1/2 less than 1, therefore diverge, but this is bigger. So these prove very hard to manipulate. If that's the case, if you're thinking of using the comparison test, then guess what? Limit comparison test is a couple of steps. How would you get a benefit out of that? You would take the dominating term divided by the dominating term. Now, this series, p equal 1, therefore diverge, is going to guarantee that this limit will equal a number. Because I chose, this was given, I chose this to be growing at the same rate as this. So this divided by 3 over n. That's the limit as n approaches infinity. And again, I'm going by the theorem. It says take the sequence part. The limit as n approaches infinity of 3 over n plus radical n times n over 3. That is the limit as n approaches infinity. Divide by the highest power term of the denominator. That will equal 1 bigger than 0. Again, therefore, both series what? Diverge by limit comparison test. Very useful test. Doesn't take that long. And how about 34? Again, I could try the comparison test, or might as well just the limit comparison test. What dominates the top? Radical n. How about the bottom? N squared. Isn't this 1 over? So if I take 2 minus 1 half, that's 3 halves. Now, this sequence is useless. You have to write it as series. This is the P series. Therefore, this converge. Now what? If I take the limit as n approaches infinity of radical n over n squared plus 1 divided, you could write it this way. You could write it this way. It doesn't matter. Those two are exactly the same. So here you're not comparing to use the comparison test. Here you're taking the limit and showing those two functions are growing, or those two sequences are growing at the same rate. So if I really look at this, this cancel with that, and I'm going to divide by the highest power term of the denominator. Again, whatever this says, this is the conclusion. Both converge by limit comparison test. Now keep in mind, I'm not listing both because I'm saying both. There is one, there's two. Comparison test, you have to say that this converge because you're introducing a different series. Well, look at this one. Something you should keep in mind. If you're dealing with a log, if you're dealing with a tangent, inverse tangent, trig, you always want to compare it with the angle or the argument. Here they're telling you that as a hint. Notice what happened if I take the limit as n approaches infinity. Now, I'm going to compare this with the argument. What dominates over the argument? 1 over n squared, right? I could say 1 plus, it doesn't really matter. But if I take 1 over n squared, and I know the series of 1 over n squared converge because p equal 2 bigger than 1. Very good. It's better to write it this way. Now if I take the limit as n approaches infinity, and what happened? What's going to happen when I take a derivative of the argument, whether it's a trig or a natural log, you're going to end up by the chain rule multiplying by the derivative of this. Since you're dividing by that, they'll undo each other. So, limit as n approaches infinity of this over 1 over n squared. N approaches infinity, that's a 0 over 0. That allows you to use L'Hopital right away. The denominator is negative 1 over n cubed. Negative 2 over n cubed, I'm sorry. So it's n to the negative 2. Bring the power down, divide by. There we go. Here, isn't that 1 over 1 plus 1 over n squared times the derivative of this? Isn't that negative 2 over n cubed? So here it is. Those cancel out every time. As n approaches infinity, this will zero out. You're left with 1 over 1 plus 0, which is 1 bigger than 0. Therefore, they both converge by limit comparison test. And there's your